Einstein's photoelectric equation for the maximum energy of emission of a negative electron under the influence of ultraviolet light cannot, in my judgment, be looked upon at present as resting upon any sort of a satisfactory theoretical foundation. Its credentials are thus far purely empirical. I have in recent years been subjecting this equation to some searching experimental tests from a variety of viewpoints, and have been led to the conclusion that, whatever its origin, it actually represents very accurately the behavior of all the substances with which I have worked. Millikan's grudging acceptance of the accuracy of Einstein's model, in spite of his personal reservations, is fairly representative of opinion at the time. The photon model was too radical a departure to be easily accepted, but it worked too well to be easily cast aside. Over time, the particle view of light became more accepted, though concerted efforts to find an alternative explanation continued until the mid-1920s. In a strict technical sense, incontrovertible experimental proof of the existence of photons was only achieved in 1977, but as a practical matter, light as a particle was an accepted part of quantum physics by 1930 or so. Both Einstein and Millikan made out well as a result of the photoelectric effect. While he's best known for relativity, the photoelectric effect is the only specific result mentioned in Einstein's citation for the 1921 Nobel Prize in Physics. And Millikan's own Nobel Prize in 1923 mentions both the photoelectric effect and an earlier experiment to measure the charge on an electron. And as we shall see, this new understanding of light paved the way for many technologies that have become central to modern life. Photoelectric technologies. The dual particle and wave nature of light is one of the classic examples of the weirdness of quantum physics, a phenomenon with seemingly contradictory properties. This is evident in the photoelectric effect itself, which relates a particle property, the energy content of a single photon, to a wave property, the frequency of the light, leading to some potential confusion as to what exactly it means for a particle to have a frequency. Even today, physicists continue to argue about the best language to describe the nature of light, and how best to teach the core concepts. As such, the idea of photons may seem too bizarre to make everyday use of. In fact, however, it is central to essentially any technology used to convert light into an electronic signal. Admittedly, the device that shows the clearest connection to photoelectric physics is a bit arcane. It's what's known as a photomultiplier tube, consisting of a series of metal plates with a high voltage, generally a few hundred to 1,000 volts, applied between them. A photon of light falling on the first of these will eject a single electron through the photoelectric effect. The high voltage then accelerates this electron toward the next plate in the series, where it collides and knocks loose several more, 10 to 20 electrons. Each of these is then accelerated toward the next plate, and the next, and so on. By the end of the tube, a single photon has triggered a cascade of millions of electrons, producing a tiny pulse of current that can readily be detected. Photomultiplier tubes can be extremely sensitive, able to detect even a single photon, and they are at the heart of many experiments investigating the quantum nature of light. While used in some older electric eye systems, these days photomultiplier tubes are generally found only in physics labs. The same essential physics, however, is at the heart of a digital camera. Each pixel in a digital camera's sensor consists of a tiny chunk of semiconductor material that is exposed to light for some period of time. In this case, incoming photons do not completely eject electrons from the material, but they do promote an electron from a state in which it is unable to move to one to where it can flow freely. More about this in Chapter 8. When the camera shutter is open to take a photo, all the electrons within a given pixel that are promoted to a freely flowing state are collected, building up a voltage that gives a measure of the brightness of the light hitting that pixel. At the end of the exposure time, these pixel voltages are read out to produce an image.